Log on, tune in, find out. Another good idea from Cambridge.
Teruhisa Tsuda, Professor Teruhisa Tsuda from Kyushu University. So there has been a change of title.
Yes.
Okay. From KP using
no,
hierarchies to Handel equation.
Thank you very much. First of all, I'd like to thank the organizers and the Newton Institute for giving me this great opportunity to speak to you, and also for giving me this chance to stay in Cambridge for 3 months. Thank you very much. And today, I'd like to talk about a certain relationship between infinite integral systems and Van-der equations, namely finite dimensional integral systems of isomonodromic type. So in this talk, I will begin by recalling some notion of KP and UC hierarchies, then show how they are related to the Van-der equations through similarity reduction. So first, I'd like to make I'd like to, where's the stick? So please look at this equation. So as an introduction, I'd like to promote this new kind of Van-der type equation, which I call generalized Gaussian system, G of Ln. Here, Fmni and Gmni is dependent variables and T is independent variables. Here you can see T0 to Tn, but without loss of generality, we can fix T0 equals 1. So it's essentially a partial differential equation in n variables. And here is the formula of the generalized Gaussian system. So it's a little complicated, but the point is that the first derivative of each dependent variables are always polynomials in f and g. So here you can find, yes, its alpha is just a constant, and large U and large B can be determined by this linear equations here. So if you solve this linear equation, then naively you imagine U and B are rational functions in f and g. But in fact, U and B are all polynomials in f and g. So this is a generalized Gaussian system. So why it is generalized Gaussian system? So firstly, if we put if with this L equals to 2, then this system is equivalent to the classical Gaussian system. It's original one. And what is the Gaussian system? Gaussian system is a nonlinear evolution equation which governs a monodromy preserving deformation of 2x2 Fuchsian system over a projective line with n plus 3 regular singularities. So, moreover, if we set large n equals 1, then this is nothing but the 6th Van-der equation. So now, I'd like to demonstrate the computation of the essential dimension of the phase space of the generalized Gaussian system here. So firstly, this expression is quite redundant in the following sense. The generalized Gaussian system is closed in fact, in the following 2NL variables here. g of a and minus a, and h. This is the ratio of f variables. So now the suffix a runs from 1 to L, and the super suffix I runs from 1 to n. So we have here two NL dependent variables. And actually, this equation is closed in these variables. Also, we can find conserved quantities written like here. So originally, the dimension is 2NL, and we find 2 times n conserved quantities. So the essential dimension of phase space is 2n times L minus 1. So for example, if we choose n to be 1 and L to be 2, this is the situation of P6, then the dimension equals 2. And as you know, the six-band equation is, needless to say, second order ordinary differential equation. And this generalized Gaussian system is actually a similarity reduction of the Yushi hierarchy, which I will explain very soon later. So now I'd like to make a brief review on the KP hierarchy and the UC hierarchy. KP hierarchy is very well known, and so I'd like to show what is UC hierarchy by comparing with the original KP hierarchy. The UC hierarchy is a natural extension of KP hierarchy in some sense. So the algebraic theory of KP hierarchy was established by Kyoto School by Sato and Date Jinbo Kashiwamiya in 80s. And so now, what is the KP hierarchy? Let us recall. So we need a set of infinitely many time variables here, x equals x1, x2, da 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 da. And let us count each time let us count the degree of each time variable xn as n. And originally, the KP hierarchy was introduced as a series of partial differential equations coming from a compatibility condition of associated linear system. But here, we will adopt the alternative definition of KP hierarchy by using only one function, tau function, and only one quadratic relation, which we call bilinear identity. So here, the dependent variable of KP hierarchy is tau equals tau x, so-called tau function. And what is the equation? The system is defined by only this single bilinear relation here. And what is large X I minus and large X j plus? Here, we introduce the vertex operator, this one, as a generating function of this differential operator. So let me show the notation which I used. yeah, this C of xz is just this function, this generating function, generating series, generating function, xn times dn. And here we substitute the derivative with respect to the time variables here. D tilde is defined by this vector. And this bilinear identity, this equation, can be regarded as a generating function of an infinitely many series of partial differential equations of Kp hierarchy. So for example, the first non-trivial member of Kp hierarchy is this one. This is the original Kp equation. And today I do not want to explain the definition of Hirota derivative, but this is Hirota derivative. And so I'd like to say that this equation is homogeneous by counting this degree counting. Then you can see this equation is homogeneous of degree 4. And likewise, we can obtain various nonlinear differential equations from this single bilinear identity. So this is the theory of Kp hierarchy. And so it is shown by Sato that the phase space, in some sense, the whole set of solutions of Kp hierarchy forms an infinite dimensional Grassmannian manifold. Today we call this Sato Grassmannian SGM. And remarkably, the set of homogeneous polynomial solutions of Kp hierarchy is filled with the set of Schur function here. S lambda is the Schur function. So in a certain sense, Kp hierarchy can be considered as an infinite dimensional integral system characterized by the Schur function. So on the other hand, the Yushi hierarchy is an extension of Kp hierarchy, which can be regarded as an integral system characterized by the universal character. Universal character is, this is a universal character, S of lambda mu. This is a generalization of Schur function attached to a pair of partitions or Young diagrams, lambda and mu. This object, universal character, was defined by Kazuhiko Koike in 80s from properly representation theoretic point of view. Anyway, now I can explain what is Yushi hierarchy. In this hierarchy, we need one more infinitely many variables. We need one more set of infinitely many time variables written as y. Here, I mean, the time variables of Yushi hierarchy is x1, x2, da 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 da, and y1, y2, da 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 da. And we set the degree of y variables as minus n. And as well as the Kp hierarchy, we can define the Yushi hierarchy by using only one function, and this time a system of binary identities defined here. So the first equation is quite similar to the original KP hierarchy, but please look at this definition of X operator. Here we added extra y derivative on the exponential function here. This is the only difference of the UC hierarchy from the KP hierarchy. And also the large y is just the same thing as x by replacing x variables and y variables each other. So this is the definition of the UC hierarchy. And what about the equation? Yes. So this equation is an example of equation contained in the UC hierarchy. This one. Here, S is a sure function with this type of Young diagram, and this is again Hirota derivative. And this equation is again homogeneous by counting the degree of variables like this. The degree of xn equals n, and the degree of yn is minus n. So this is again homogeneous. And it is obvious from the definition of the hierarchies, both KP and UC hierarchy are homogeneous. They have some homogeneity. This is an important point. And actually, so in other words, we can say that the UC hierarchy will generalize the KP hierarchy by introducing the negative time flow besides the positive time flow x, while keeping its homogeneity. And as analogous to the KP theory, the phase space of UC hierarchy formed a direct product of two Sato Grassmannians, and also the homogeneous polynomial solutions is always the universal character. No, the homogeneous polynomial solution of UC hierarchy is characterized by the universal character. And the naming is coming from by taking the initial letters of universal character. So this is a very brief review of KP and UC hierarchy. So moreover, we can deduce from the original binary identity more various binary identities. One of them is called modified hierarchy. Very roughly speaking, modified hierarchy is a binary identity for contiguous tau functions connected with application of vertex operators. So for example, this is a well-known modified KP equation, modified KP hierarchy, and the tau n and tau n plus 1 lie on the chain, and each vertex is connected with the action vertex operator, very roughly speaking. And on the other hand, for UC case, we have two kinds of vertex operator, and they mutually commute. So we can arrange the tau function on the two-dimensional lattice M and N. So this is a typical bilinear identity contained in the modified UC hierarchy. This one. So for example, this is a typical equation coming from the modified UC hierarchy. This one. This is a differential difference equation. Here, delta t is a vector field defined by this formula, and the bracket t is just this vector. So anyway, I'd like to enter into the main subject of this talk. So the conclusion is that monodromy prismatic deformation equation or Pan equation can be obtained from the KP or UC hierarchy through similarity reduction. So what is similarity reduction? Similarity reduction, principal ingredient of similarity reduction is homogeneity, periodicity, and specialization. So for example, let us consider the reduction from UC hierarchy to the generalized Gaussian system. So first one, this is a homogeneity. Here, E is an Euler operator, defined like this, and dmn is some constant parameter. And here is the periodicity. This condition is posed in order to reduce the dimension of the phase space to obtain the finite dimensional integral system. So, and of course, this equation, KP or UC hierarchy, has infinitely many time variables. So we need to make a specialization on the time variables. In this case, we set xn and yn as a power sum here. This is just a power sum with the constant coefficient theta. Xn is positive power sum and yn is defined as negative power sum. And now, I'd like to let us show some advantages of the similarity reduction in Pan equation. So firstly, Hirota bilinear form for tau functions. The KP and UC hierarchy are defined by the bilinear identity. So it's a priori bilinear form. So this is obvious. And as you know, KP and UC hierarchy has a homogeneous polynomial solution written in terms of sure function or universal character. So rational or algebraic solutions of Pan equation written by sure functions or universal character can be obtained immediately. And the corresponding tau function define so-called the special polynomial of Pan equation. So-called Umemura polynomial or Okamoto polynomial, and very originally Jablonski-Borovev polynomial were known. And the third is wire group symmetry of type A. This is originated from some permutation of vertex operators. But today I do not enter into detail here. And the last one is it's the most important among them, Lux pair. So for KP, we can define the wave function psi n. This is a function in x and k. K is an extra parameter called spectral variables, defined as the ratio of tau functions and the exponential function here. So this is the usual wave function of KP hierarchy, and we can deduce all the associated linear equation of KP hierarchy from the bilinear identity. On the other hand, for UC case, we can define the wave function psi of mn of xyk as well. So we can automatically obtain the Lux pair for Pan equation from the bilinear identities. So here is a result. So for KP case, if we choose L equal to periodic, this is KBB case, and the specialization is xn equals 0 for and not equals to 1 and 3. And this means that the first, except the first non-trivial proof, we eliminate all the time variables. Then the resulting fundamental equation is P2. It is very well known from Abrovitz-Seeger and Flaschka-Newell's work. And here is the corresponding Lux equation in the spectral variable. This is 2 by 2 system with one regular singularity and one irregular singularity with Poincare rank 2 over 3. No, 3 over 2. And in this case is also well known from the work of Nomi Yamada. The resulting fundamental equation is so-called the higher order fundamental equation of type A. And L equals 3 cases correspond to P4 and L equals 4 cases correspond to P5. And this is the corresponding linear equation. And this is a new one. If we set the variables here, then obtain the resulting fundamental equation is the P3 chain, which includes the original P3 as the case of L equal 2, and with this singularity data. And how about the UC case? We can set LL periodicity for UC. Then, this one, so I skip here. And this is the specialization corresponding to the generalized Gaussian system, as I mentioned. And here is the GLN, the generalized Gaussian system. L equals 2 case is the Gaussian system. And moreover, if we put n equals 1, then this is the ordinary differential equation case, and the resulting fundamental equation is the 6th fundamental equation. So how about the corresponding linear equation? This is L by L Fuchsian system with n plus 3 regular singularity. So thank you very much for your kind attention.
So in your L times L system corresponding to GLN, these n plus 3 regular singular points, do the residues have all distinct eigenvalues, or is there some multiplicity in the eigenspaces?
Yes, your question is that what is the spectral type of the Fuchsian system?
Yeah.
Yes. Yes, I think actually I have way better for your questions. In this case, the corresponding spectral type is 1, 1, 1, 1, 2, and L minus 1, 1, and n plus 1. The spectral type describes how the exponents are reduced. So this means all the exponents are distinct. And in this case, L minus 1 exponents are same, the same value, and 1 is distinct. So in L equal 2 case, this is general Schrödinger system. But if L is more than 3, it's a subfamily of the Schrödinger systems.
Any other questions? Thank the speakers, Master.